Chapter 2, Digital Image Processing. We discussed the major components of a digital imaging system in the previous chapter, which included data acquisition, image processing, and image display, storage and archival, and image communication. Remember, with data acquisition, this refers to a systematic method of collecting data from the patient. In CT, data are electron density of tissues, which is attenuation data. And the components include the X-ray tube and the detectors. The output signal from the detectors is an electrical signal or an analog signal that varies continuously in time. The digital computer converts the analog signal to a digital signal for the processing, and this conversion is performed by the analog to digital conversion, or the ADC. For the image processing part, this is performed by the digital computer, and it takes an input digital image and processes it to produce an output digital image by using the binary number system. The binary number system uses numbers that are zeros or ones, and these numbers are called bits, or binary digits. The ADC then sends the digital data for the digital image processing by a digital computer. For the image display, storage, and communications part, the output digital image must be converted into an analog signal before it can be displayed on the monitor. And this is done by digital to analog conversion, or the DAC. The image can then be stored and communicated electronically through computer networks, such as PACS. The history of digital image processing dates back to the early 1960s when NASA took analog images by a television camera and converted the images into digital images, which were then processed by the digital computer to obtain more information about the moon's surface. Images are classified on the basis of their form or the method of generation. Images are a subset of all objects. Within the set of images, there are other subsets, which include visible images, optical images, non-visible physical images, and mathematical images. As far as image formation and representation goes, there are analog images and then digital images. Analog images are continuous images. They include chest x-rays, since it represents a continuous distribution of light intensity as a function of a position on the radiograph. In radiology, the film is processed in chemical solutions to make them visible, and the images are formed by a photochemical process, where the images are represented as electric signals that emerge from the photoelectronic device. Digital images are numerical representations or images of objects. This requires a digital computer, and it needs analog to digital conversion, which converts the continuous signals to digital signals. And here the computer receives the data and processes it, and then displays it as a digital image. Check out Figure 2.3 on page 30 of your textbook. So we know from previous slides that there has to be a conversion from an input image to an output image during image processing. If both the input and the output image are analog, then this is considered analog processing. Digital processing is when both the input and the output image are discrete. And in digitization, the analog image must be converted to digital data for input into the computer. So all images can be represented in two domains, which are based on how the images are acquired. These two domains are spatial location domains and spatial frequency domains. All images that humans can see, such as radiography and CT images, they are in the spatial location domain. A digital image is arranged by the location of each number in the image using the XY coordinate system. The x-axis describes the rows or lines placed on the image, and the y-axis describes the columns. For example, the spatial location 6, 7 describes a pixel that is located 6 pixels to the right of the left-hand side of the image and 7 lines down from the top of the image. So images can also be acquired in the spatial frequency domain, and these are MRI images, for example. The term frequency refers to the number of cycles per unit length, that is, the number of times the signal changes per unit length. There are small structures within an object, and these produce high frequencies and represent detail, and then there are large structures which are low frequencies and represent the contrast. Digital image processing can transform one image domain into another image domain, and this can be done by use of a Fourier transform. It converts the image in the spatial location domain to an image in the spatial frequency domain, and this allows the enhancement of certain image characteristics to be made visible. The structure of a digital image can be represented by several factors, which include the matrix, pixels, voxels, and bit depth. The matrix is a 2D array of numbers, and it's made of columns represented by M and rows represented by N that define square regions, which are pixels. The size of an image equals M times N times K bits. K bit stands for kilobits, which is a multiple of a bit, and remember we discussed bits a little bit in chapter 1. When M equals N, then this means that the dimension is perfectly square. Usually diagnostic images aren't square, but are rectangular in shape. The radiology tech selects the matrix size when they are imaging a patient, and this is often called the field of view. 512 by 512 is the typical field of view for CT. The larger the matrix, the longer the processing time and the more storage space that is necessary. And the longer the transmission time for the communication. So image compression is often necessary for the storage and transmission requirement. Pixels are another factor of the digital image, and the pixels make up the matrix and are usually square. Each one contains a discrete value or number representing a brightness level, and the numbers represent tissue characteristics being imaged. So for example, in CT, these numbers are related to the atomic number and the mass density of the tissues. Pixel size can be found by the field of view divided by the matrix, and the larger the matrix size, the smaller the pixel size for the same field of view, and the better the spatial resolution. Voxels are another factor of the digital image, and voxels are pixels representing a volume of tissue, or a volume element. The voxel information is converted into numerical values contained in the pixels, and these numbers are assigned brightness levels. The high numbers means that there is a high signal intensity from the detectors, and this is represented with a white color, and the low numbers means that there is a low signal intensity from the detectors, which is represented by black color. Then there is a range of grayscale colors in between, ranging from black to white. Another factor of a digital image is bit depth, and this is the number of bits per pixel. The binary number system uses a base 2, so kilobits equals 2 to the k power. And this just means that each pixel will have 2 to the k power of gray levels. So for example, a bit depth of 8 means that each pixel will have 2 to the 8 gray levels, or 256 shades of gray. The higher the bit depth means a better image quality. So a higher matrix size means that there is a better spatial resolution on the image. Lower the pixel size also means a better spatial resolution. And the higher the bit depth equals better contrast resolution. The primary objective during image digitization is to convert an analog image into numerical data for processing by the computer. Digitization consists of 3 steps: scanning, sampling, and quantization. For the scanning step, this is a division of the picture into small regions, and each small region is a pixel, so essentially, scanning results in a grid made by rows and columns. The size depends on the number of pixels on each side of the grid, and the higher the number of pixels equals the better image detail. For the sampling step, this measures the brightness of each pixel in the entire image. A small spot of light is projected onto a transparency and is detected by a photomultiplier tube positioned behind the picture. The output of the photomultiplier tube is an electronic signal. For the quantization step, this is where the brightness value of each sampled pixel is assigned an integer or a gray level, and the result is a range of numbers of gray levels, and each one has a specific spot on the grid of pixels. The lower the number, the darker the shade, or the more black it is. The higher the number, the brighter the shade, or the more white it is. And this depends on bit depth, and the value of the integer is directly proportional to the signal strength. So the higher numbers have higher signal strength, and lower numbers have lower signal strength. The result of quantization is a digital image, an array of numbers representing the analog image that was scanned, sampled, and quantized. And the array of numbers is sent to the computer for further processing. As we know by now, the conversion of analog signals to digital information is accomplished by analog to digital conversion, or ADC. And the ADC samples analog signal at various times to measure its strengths at different points, and the more points sampled means a better representation of the signal. The sampling process is then followed by quantization. Two important characteristics that are inversely related are speed and accuracy. Speed is the time taken to digitize the analog image, and accuracy refers to sampling of the signal. If there's not enough samples taken, then the representation of the original signal will be inaccurate after the computer processing, and then aliasing artifacts occur. The more parts to the signal, then the greater the accuracy of the ADC. Measurement unit for parts is the bit. This can be a 0 or 1, remember. For example, an 8-bit ADC generates 256 equal parts because 2 to the 8th power equals 256. And the higher the bit number, the more accurate the ADC. So the greater the accuracy, then the longer it takes to digitize the analog signal. Why digitize images? For image enhancement. This is just one reason. The purpose is to get an image pleasing to the observer. It includes contrast enhancement, edge enhancement, spatial and frequency filtering, image combining, and noise reduction. Another reason is image restoration. And the purpose of this is to improve the quality of images that are distorted or degraded, which includes blurred images. Another reason to digitize images is for image analysis, which allows measurements and statistics to be performed. And it includes segmentation, feature extraction, and object classification. Another reason to digitize images is for image compression, and the purpose is to reduce the image size to decrease the transmission time, and also to reduce the storage space. So this is especially useful in the PACS world, where the image data sets are large, especially from CT and MRI images. There are two types, lossy and lossless. Lossy is where some loss of image detail happens when the image is compressed, and lossless is where no loss of the image information and detail occurs. Another reason to digitize an image is for image synthesis, and this is where you create images from other images or non-image data. This is useful when an image cannot be acquired, and this includes image reconstruction and 3D visualization techniques. Image processing techniques are based on three types of operations: point operations, local operations, and global operations. And the algorithms that these operations use alter the pixel intensity value. Point operations is the most frequently used image processing technique, and the value of the input image pixel is mapped on the corresponding output image pixel. And algorithms are used, and they allow input image matrix to be scanned pixel by pixel until the entire image is formed. Gray level mapping, or windowing, is the most common point processing technique, and it uses a lookup table, or an LUT, and the lookup table plots the output and the input gray levels against each other. This changes the brightness of the image and increases the enhancement of image display. Windowing also modifies the histograms. Histograms are a graph of pixels in all or part of the image and are plotted as a function of a gray level. And this indicates the overall brightness and contrast of an image. Wide histograms means that there is high contrast, and a narrow histogram means that there is low contrast. Then there is local operations, and this is where the output image pixel value is determined from a small area of pixels around the corresponding input pixel. Check out figure 220 in your book. Spatial frequency filtering is used, and it involves the brightness information in an image. When the brightness changes rapidly, the image has high spatial frequency. And an image with smaller pixels has higher spatial frequency. So still discussing local operations, convolution occurs, which this is a technique of filtering in the spatial domain. The value of the output pixel depends on the group of pixels in the input image that surrounds the input pixel of interest. The new value of the pixel of interest is calculated by obtaining its weighted average and that of its surrounding neighboring pixels. The average is then computed by using a convolution kernel. So this is just an example of how the convolution kernel works. First you start out with your source pixel right here, and then your convolution kernel moves across the image pixel by pixel to compute the value of the corresponding output pixel. So it looks at the neighboring pixels of the source pixel, and then it computes the value of the corresponding output pixel. Also in local operations, there is high-pass filtering. High-pass filtering sharpens the input image in the spatial domain that appears blurred. Then there's low-pass filtering. The low-pass filter is used to operate on the input image in order to smooth the image. The output image appears blurred, and the smoothing reduces noise and displayed brightness levels of pixels, but it does lower the detail. Unsharp masking is another local operation, and this uses the blurred image produced from the low pass filtering process and subtracts it from the original image. So this then makes the output image appear sharper. And in this example of this picture right here, the bottom half actually has the unsharp masking applied. So you can tell that that bottom half is sharper than the top half of the image. In global operations, this is where the entire input image is used to compute the value of the pixel in the output image. And a Fourier transform is an example of this, where it provides edge enhancement, image sharpening, and image restoration. Another image processing technique is geometric operations. Geometric operations modifies the spatial position or the orientation of pixels in the image. The algorithms that are used, they change the position of the pixel instead of the intensity. And this results in scaling and sizing of images, image rotation, and translation. CT image sets can get to be very large, which makes it hard for transmission and communication of the images, and this is where image compression comes into play. In image compression, you use software or hardware techniques to reduce information by removing unnecessary data. In decompression, the equipment later decodes the information and fills in the representation of data that was removed during the image compression. And remember, there are two types. There's lossless. This is reversible, and it does not involve quantization. And there is lossy, which is irreversible, and it involves at least 3 steps: image transformation, quantization, and encoding. It provides high compression ratios compared to the lossless compression. So as the compression ratio increases, the less the storage space is required, and the transmission speeds are actually faster.